The title for my presentation is Case Study of In-Cab Pollutants for Non-Road Construction Equipment. My name is Phil Lewis, and I'm an associate professor at Texas A&M University in the Department of Construction Science. My co-authors are Rachel Mosier and Yongwei Shan from Oklahoma State University. Indoor air quality in construction equipment cabs may be affected by many things, especially the environment in which they work. The environment includes the climate, such as the temperature and humidity at the job site, and the job site itself, such as dusty and dry conditions. Other sources of air quality contaminants may include the equipment cab itself, especially diesel exhaust, and then other sources that impact the air quality could be what the equipment is doing, so the equipment activity, and then also operator activity, such as smoking in the equipment. Although there are no permissible exposure limits for diesel exhaust related to heavy construction equipment, there are both short-term and long-term health effects associated with breathing in diesel exhaust. Some of the short-term effects include ear, nose, and throat irritation, dizziness, headaches, and fatigue. Some of the long-term health effects include respiratory illness, heart disease, and cancer. The objective of our case study was to collect and analyze real-world pollutant data inside cabs of heavy-duty diesel construction equipment. Specifically, we were trying to collect data for carbon monoxide, carbon dioxide, and particulate matter, PM 2.5. So all of these may come from diesel exhaust and can come from diesel exhaust, but they can come from other sources as well. And in our study, we did not make a distinction from the source. So what we did is we merely collected the data from inside the cab, and we did not determine whether it came from diesel exhaust or from some other source. The way we collected the data was using this instrument shown here, the EVM7 Advanced Particulate and Air Quality Monitor. This monitor was used to collect samples of CO2, CO, and PM 2.5. It can also collect data related to temperature and humidity, but we are not showing those results as part of this particular study. We actually used two of these instruments so that we could collect data from two items of equipment each day. This is a summary of the equipment that we tested. It was 15 items of equipment in all, including one backhoe loader, 4 excavators, one rough terrain crane, one scraper, actually 2 scrapers, and 2 wheel loaders. And this equipment was used on a residential development project near Stillwater, Oklahoma. Here's a sample of the air pollutant data that we collected. In the far left column, you can see the test dates in which we collected this information. Most of this information was collected during the fall and actually during the fall and winter of 2016 and 17. You can also see that we collected the data for CO, CO2, and PM 2.5. The data for CO and CO2 is in parts per million, and the data in PM 2.5 is in milligrams per cubic meter. Looking first at carbon monoxide, you can see that the minimum value in each case was 0. And then the maximum value ranged from 0 up to 6 parts per million. And that was in excavator 2 and scraper 3. The averages or the mean values range from 0 up to about 1.4. So you can see that there's a lot of variability in the CO data inside the cabs of the equipment. And it's also worthwhile noting that the data for CO tended to rise and fall during the day. So sometimes it would be high, sometimes it would be low, and it was not consistent. For CO2, you can see that the minimum values were all right around 300 parts per million, and the maximum values went up close to 2,000 parts per million. The CO2 values probably mostly were impacted by the exhaust from the diesel equipment itself, coming from the exhaust stack, but also from the equipment operator inside the cab as he exhaled. The PM 2.5 data ranged from 0 as a minimum up to 6.43 as a maximum. So we see a lot of variability in the PM2.5 data as well. You can also see the mean values. The mean values shown in this table are based on 8 hours of data collection. So we place the EVM7 inside the cabs of the equipment first thing in the morning, and then we let the equipment operate all day long, and then we remove the monitor at the end of the workday. So as I mentioned, there are no specific permissible exposure levels for CO, CO2, and PM2.5 specifically rated to diesel exhaust. So what we did is we assumed or made the assumption that the equipment cabs represented an indoor air quality environment. So we used IAQ standards for comparison. So for example, one standard we found was from Health Canada residential standards. The CO level there would be, the maximum level would be 11 parts per million. When we compared our data to that, we saw the CO levels in the cabs increased and decreased during the day, but none exceeded 11 parts per million. So we did not violate that Health Canada residential standard. For CO2, we saw one standard from EPA Building Air Quality Guide for 1,000 parts per million. And so this level represents inadequate ventilation in buildings. So anytime that the CO2 level exceeds 1,000 parts per million, then there's going to be, that represents inadequate ventilation and can basically imply some thermal discomfort. So here inside the cabs, we saw that 11 of 15 tests exceeded that 1,000 parts per million limit. We found both a short-term and a long-term standard for PM2.5, both coming from Health Canada. The short-term standard was 0.1 milligrams per cubic meter. And it's interesting here to point out that all tests had maximum values that exceeded that short-term limit. And then for the long-term exposure limit, which would be for 8 hours of 0.04 milligrams per cubic meter, we found that 7 of 15 tests had 8-hour averages that exceeded this level. So we can see here that PM2.5 is most likely the pollutant of most concern that we tested. Conclusions. Due to the potential health, safety, and productivity consequences of CO, exposure for equipment operators should be monitored. So for CO, there are some concerns breathing that in. It can lead to lightheadedness, dizziness, and that is not a good situation for equipment operators. In worst cases, it could lead to death, although in ambient conditions, that's not likely. Although CO2 exposure is primarily a comfort issue for the equipment operator, it still has the potential to serve as a distraction, which may reduce productivity and pose a safety threat. So if the equipment operator is more concerned about comfort inside the cab, that's probably less time they're going to have to focus on being productive. And then PM2.5 exhibited the greatest potential to be a health threat to equipment operators. Again, we did not make the distinction between the PM2.5 that came from the tailpipe of the equipment versus the dust. I think it's safe to say that most of the PM2.5 measured inside the cab is coming from the dust at the job site. Some limitations and recommendations. Basically, we only have 15 data points and we need more tests, and we need to test more equipment to increase the statistical power and robustness of our studies. We also want to characterize equipment and its activities during those tests. So what was the equipment doing? What activities was it involved in? Is there anything that we can use to identify any certain activities we can identify as being more or less safe for the equipment operator? And then also characterize the operator behavior during the test itself. So was the operator smoking or eating inside the cab, or was there any other activity? So we do have other studies where we're attempting to collect more data, and in the future we hope to have more information regarding this important topic. Thank you.